Hello guys, welcome to the YouTube channel, and today we'll be covering the topic CAE, Computer Aided Engineering. And for those of you who do not have a prior knowledge regarding CAE or are about to study about the CAE in their college, then this is the video for you. We won't dwell much deeper into the topic of CAE. We will just try to deliver a basic understanding about the topic, and we'll also be answering some of your questions. That is the role of CAD in CAE, that is computer aided design in computer aided engineering, and also what does the analysis software do in the background. So without further ado, let's get started. Computer aided engineering. The computer aided engineering is nothing but the broad usage of computer software to help in the engineering analysis tasks. It includes finite element analysis, computational fluid dynamics, multi-body dynamics, and optimization. So we will be looking at these multi-body dynamics optimization in the subsequent slides. So what is the finite element analysis? Finite element, we do in the finite element analysis is we divide the whole geometry into elements and nodes. The whole geometry, as you can see here, it is divided into small element and nodes. So the software will carry out study at the nodal point and then interpolate the result for the element, and the element then interpolate itself to the for the whole geometry. So as we already knew about the partial differential equation, what is the partial differential equation and what does it represent? The partial differential equation or the differential equation nothing but to represent the changes, equation which represent changes, such that if I have to predict how the population is increasing or decreasing every month or every year, I can use differential equations. But I cannot predict the exact value of how much population will be reached by the year 2022. But I can tell what is the rate at which it is increasing or it is decreasing. So that is the partial differential equation, and it is considered to be the most complex equation to be solved. So computers are considered to be the most sophisticated device. We've been using computers since decades now, and for this type of task to be performed or this type of analysis to be carried out, we've been using computers. So we've been performing finite element analysis since decades without computer, and now in this era we're using computers to solve for the partial differential equation. So now that you have a basic understanding of computer aided engineering, let's look at what is design validation. So design validation means whether the component which we are going to manufacture or which we are going to produce in the market will sustain for various loading conditions or not. Now any product that you are about to manufacture, the product has to go through various testings. That is nothing but the validation. And if the product survive or if the product stipulates that testing, then it is considered to be a good design and the design got validation. Any product which is launched into the market has to go through various testing. If the product is not tested thoroughly, then the customers are going to return back to you, and that causes defamation of the company. So the picture which you are seeing here is of the iPhone 6. The iPhone 6 was claimed by the Apple that it was the most slimmest smartphone in that 2013 era, and it was indeed the slimmest smartphone. I had that too, and there are many customers who are coming back to Apple Store saying their iPhone got banned into the pocket. So which is true. You can look it up on the internet that many customers have faced the issue that their iPhone got banned in their pocket. So Apple for sure considered it and faced the criticism, and then Apple the company redesigned it, and they have changed the composition of aluminum. They have added some amount of copper into it, and then they have again launched with the name as iPhone 6s. The iPhone 6s also features like a 2 GB RAM. In the iPhone 6 it was 1 GB, but yeah, the problem was solved, and this is what happened when you do not validate your design properly, when you do not apply the proper loading condition to find out the result. So in the using computer aided engineering, we've been validating design since decades now. So there are three methods to validate any design. The first is analytical method, and the second is numerical method, and the third is experimental method. So we'll be looking at analytical method first. The analytical method, beside having the advantage that it will give you 100% correct result, but it is considered to be the hardest method because it's not easy and you have to have formula of each and every equation or each and every condition. For each and every condition you have to have the formulas, and it is for sure time consuming, and you cannot accuracy can be believed blindly. You have to solve for multiple time for the same problem, and this is the method we've been performing in the say 3 to 4 decades ago. Now that we have computers, we no longer perform this and we perform this numerical method. So in the numerical method, this is nothing but the CAE. We includes computer into the solving of partial differential equation, and this is how we predict the forces and loading and find out results. So what is the advantage of numerical methods? That we can solve real life complicated problems. The results can't be achieved, the results can be achieved faster. Results can be achieved on entire geometry. That is, you have to just provide the boundary condition, correct boundary condition, and then you do not have to take care of that each and every point. The software is going to do it for you. And applicable even if a physical prototype is not available, so we just have to make the CAD file. We have different softwares, SolidWorks, AutoCAD, and many softwares that you can make CAD out of many softwares. And then for the analysis software we have Hypermesh, we have ANSYS, and also SolidWorks and KTR, they are also providing, but I don't think you should opt for SolidWorks, or since their accuracy is quite low, and if you want to taste the real CAE, then you should opt for Hypermesh. So the picture which you are seeing is of my guitar, and the guitar broke from a very unusual place. The guitar usually breaks from bridge, that is here. Here, the guitar usually break from this. The bridge got sheared in the usual case, but this guitar broke from the neck, which is very unusual. So I have performed a CAE of it, and I made a CAD file of it first, and then I have meshed it and performed CAE. So the result which I have got was usual. The guitar broke from here, but this is not the picture of it. In this picture the guitar broke from here because I have provided the wrong boundary condition. I have provided the static boundary condition previously. That is why I'm getting a breaking from here, that is from the bridge. But then I've thought about it, and I have studied thoroughly that the loading, that is the when I play the guitar, it it won't be any static loading. The loading will be changed as I apply force on the string. The tension in spring increases, and this causes the guitar bridge to compress. So that compression is not static, it is time variant. Whenever I apply force, then only the string tension gets increased. So this is the reason I have applied then transient loading, that is the loading which was changing with respect to time. And then here are the result which I've got. You can see it is exactly the same position where the guitar break. The stress concentration at here is quite high, and that's where the guitar breaks. So this is why you should always opt for numerical method, even though they give approximate result. But if you apply the proper boundary condition, then the result which you are going to get is very much likable. And the third method comes up to be experimental. Now it's quite common and it is often performed. Even though we are using numerical methods, it's not that we are not using experimental method. Experimental method is a phase the component has to go through, and it is for sure after the prototyping this phase exists. It still exists, and still you can see the car here. This is the organization which does it is NCAP. They provide the rating of the car based on their safety, and yeah. So talking about the CAE, we have 4 numerical methods, or talking about the numerical methods that we have seen earlier, here we have 4. depend on the what type of result you want to get. If you want to get the stresses, strains, displacement and corresponding value, that is fatigue life and stuff related to it, then you should go for finite element method. And boundary element method, if you are interested in the frequency output, that is how much the displacement is changing with respect to applied frequency and or transient loading, then you should opt for boundary element method. And finite volume method, we all know about the computational fluid dynamics, in which the single volume is considered. The in That is the finite volume method, conservation of momentum receiver. We will look it up about in the subsequent slide. And then there are finite different method. The finite different method is nothing but the combination of two of the above method, that is finite volume method or boundary element method, or finite volume method or finite element method. So combination of the above three, any two of above three. So first we will be looking at finite element method. So the finite element method, FEM, is a numerical technique for finding approximate solution to a boundary value problem for partial differential equation. It is also referred to as finite element analysis. So in the finite element analysis, what we do is we first generate the CAD file of whatever the component which you are about to manufacture or which you are about to analyze, and then we divide that component into multiple elements, set of elements. As you can see here, I have a CAD file, I have made it on SolidWorks, and then I have imported that CAD file into our Hibernate software, and then I have meshed it, that is divide the whole geometry into into elements and nodes. And then I have applied the boundary conditions, that is I have applied forces, and I have given the condition that where will my object be constrained, and I have performed the analysis. Then the software gave me the result which is 100% accurate. The next comes up to be boundary element method. Boundary element method is most often used as an engineering design aid, similar to the more common finite element method. But the BEM, that is boundary element method, has a distinction and advantage that only surface of the domain needs to be meshed. So in this boundary element method, we are only going to mesh the surface. We do not need to mesh the whole geometry. We just need to make create surface of the geometry, and then we have to mesh that geometry. Only surface, no need to go into the bulk, only surface. So for what the analysis which is related to frequency, or you want to know the frequency, that is random response analysis, frequency response analysis, and radiant power. So this type of analysis is usually carried out through boundary element method, or they comes under the boundary element method, in which we only measure the surface of the geometry, we do not measure the whole geometry. So yeah, if you want to know the frequency output or the time variant output, then you should really opt for boundary element method. Then the third one is finite volume method. Most computational fluid dynamics is based on the FEM. The unit volume is considered in the finite volume method. Variable properties at the nodes include pressure, velocity, area, mass. It is based on the Navier-Stokes equation. I presume that most of you know about the Navier-Stokes equation. They are nothing but the differential equation which will give you an idea about how the fluid is flowing around a particular object, or how the fluid is flowing in a free stream. So the Navier-Stokes equation gives an idea about it. So as you can see in the first image, the car, how the software predict how the air is flowing across the car. So if you know how the air is flowing, and you can guide the air, so you can change the drag coefficient and lift coefficient through it. So that is used to optimize the car design. And in the second image we have a aerofoil shape. Now aerofoil shape, we've been using aerofoil shape for a year, but we do not really know how the aerofoil is, we do not know the exact science behind the aerofoil, and there are many research which we always read about it, but none of them claim to be the 100% right. As you can see here in this image, the pressure, it's quite low at the top of the aerofoil and it is significantly high at the bottom of the aerofoil. That point where the pressure is zero is considered to be the stagnation point. It is called the stagnation point. And this is the reason behind the lift of the aeroplane. Why the aeroplane fly? Because the pressure here is quite low and the pressure here is quite high. So the heat region here is kind of vacuum, and because of the pressure difference we get the lift. So yeah, if you want to, if you are interested in studying that type of analysis, you should go for the computational fluid dynamics. Finite difference method. Finite difference method are, as I already discussed, nothing but the combination of two methods, that is computational fluid dynamics or BEM, or computational fluid dynamics or finite element method. So in this image, uh, if we want to know how much stresses is generated on the wing of an aeroplane, so in order to know how much stresses is generated, we must know the forces acting on it. And how could we know the forces on it, since it is an air, the force applied by the air? You have to, for that you have to perform the computational fluid dynamics. What the computational fluid dynamics will do, it will give you an idea about the pressure difference, and then once you know the pressure, you can apply boundary finite volume or finite element analysis, since you have the pressure and you can find the stresses. So it's nothing but the combination of two methods. Now the question, what does the CAE software do in the background? So the CAE retrieves description in geometry from a CAD database. CAE software and CAD base, they do not work on the same platform. You have to create CAD file first on a different platform, and then you have to perform the analysis on a different software. The way I do it is, I made the geometry, that is CAD file, in SolidWorks, and then I export that CAD file into the Hypermesh software, that is a CAE software. So what you are doing in the CAD is, you are nothing but setting up the metrics. Suppose you made a cube in a SolidWorks or AutoCAD or many softwares, Pro-E, CATIA. You made a cube in that software. So the way we see it is cube, that is for our simplification. But what the software understand is this. This is the representation of this cube, are nothing but the coordinate point, different coordinate points on different axes, and this is what the software understand. So in the CAE software, the CAE software considered this as the stiffness matrix. The software going to perform operation on this to find out the displacement, stress, and strain, that is the corresponding value. So we'll be looking at it. And the basic finite element equation to be solved for structure experiencing static load can be expressed as Ku equal to P. Now what is K, what is U, what is P? We already knew K, that is the stiffness matrix that is being defined in the CAD software itself, as you can see here. And what is U? U is displacement. We do not know the displacement yet, so U is unknown. And what is P? That is the boundary condition, such that I have applied a load in the x direction. So that magnitude of that load is nothing but to be P, that is the force. So we have two terms known and one term unknown. We can easily calculate, although we are not going to calculate it, software is going to calculate this for us. U is nothing but the displacement. The software is going to transfer this to here, and so the final equation will become U equal to K inverse of P. Oh, K inverse P. K inverse means this is the stiffness matrix, and this will go here, that is on the right hand side, this will become the inverse of K. So P inverse of K, the software is going to find out the inverse of the matrix and then multiply that matrix by our load factor, that is P. So what you will finally get that here is the deformed stiffness matrix. Deformed stiffness matrix means the value of displacement, how much because of this force the stiffness matrix changed, by what amount. So we are going to get that value. That value is going to be u, that is the displacement. And now that we have u, that is displacement, we can calculate the strain. How? Because strain is nothing but the ratio of change in length upon unit length. We know the change in length, that is displacement, and we know the initial length from the geometry itself. So the strain is calculated. Now that we have strain, we need to calculate the stress. Again, the value of E, that is Young's modulus, is known, or the uh, Hooke's constant is known. We will multiply that using, this is nothing but the Hooke's law. We multiply the strain into the value of Young's modulus, and we will get the value of stress. So all this calculation, you do not know, you do not need to take care about it. The software is going to take care about it. You just need to provide the right boundary condition. Just like here we have, I said that in this direction the software is going to be we are going to apply force. You just need to take care about it. And that is all about the CAE. If you want to know much about it, I will be uploading a video related to it. And yeah, thank you for your time. Thank you.